Hello, welcome to session number 3 in the playlist Electrodynamics. And here we are going to do something now. We have looked at a lot of theory stuff. So now we are going to work with ADS here. And ADS, there are other playlists where I have covered how to use ADS and all that stuff. So here I'm just going to make a new workspace, which is also called a project in ADS, and I'm going to call this as LTCC designs. So better not have any white space characters other than underscore. Okay, so this is called LTCC designs, and I am not going to set any I'm not going to attach any technology files here, right? So I'm going to leave it blank. Okay, and but I'll still set the layout resolution, so I'll check that and just say create workspace. Okay, so now this comes up, which says that what should be the resolution for layouts, and I am going to choose I can draw in mils, I can also draw in millimeters, so I'm going to choose millimeters here, right, and say let me see, yeah, that's fine, millimeters is okay, and say finish. Okay, so once we are done with this, we have a blank empty workspace over here. Now the first thing is I am going to create a substrate, right? And for that, what I can do is I can right click and say new, and I can say substrate. Okay, so now I'm going to define what should be the metal stack, right? So here I'm going to call this one as ferro A6S. So this is going to be your all silver substrate. Your template can be anything, doesn't matter, just say create, and it directly opens a window here which allows you to add some components. So now a little bit of background here. I'm going to make 7 metal layers or 8 metal layers, and so I will need 7 vias to connect in between them. So now why 8 metal? Well, it's up to you to choose how many metal you want to use, right? So I'm going to use 8 metals, and as I told you about processing, you have a choice how many green tapes you apply, right? I'm going to apply 7 of them, so that will make 8 metal layers. Okay, so this we have to create because the metals which are already defined, okay, they don't have this list from M0 to M7, VR0 to VR6, it's not there. And then there is thick your thin film resistor here. Okay, so this is what we have to define. So now if you see the right hand side, what's the process role? The process role for M0 to M7 is that it's a conductor. The process role for VR0 to VR6, it's a via, right? It's a conductor via. And TFR or thin film resistor is also a conductor. So let's do that first. Okay, so first of all, what I'll do is I will go to okay, I'll go to layer, right, layer definition. Here is where I can add different layers, right? So I'll go to layers and I'll say add layer. Okay, it is recommended to add layers directly from the substrate editor. That will allow you to map these layers. Yes, I know that. Okay, I don't need that. I know what I'm doing, right? So what I'm going to do is add layer. Okay, so I have added already 2 layers, right? 39, 40. So I will name this as M0, and that's a conductor layer, right? Then I am going to name this as M1. Okay, that's a conductor layer also, right? So I'm going to keep adding these layers up to I reach M7, right? M2, M3, M4, M5, and then 2 more, M6 and M7. So these are all conductor layers, right? So if you see the role here, it says conductor. Then I would add few more layers, namely 7 of them. 1 2 3 4 5 6 7. Okay, so this is going to be via 0. So I'm going to name via 0 as a via between metal 0 and metal 1. So the lower metal gets the descriptor 0, right? So I will call this as via 0, and this is a conductor via. Similarly, via 1, it's going to be a conductor via. Via 2 is again conductor via. Via 3 is a conductor via. Via 4, and I'll tell you what exactly that is. Now, as I told you that this momentum is a 2.5D simulator, so its editor is also 2D. So how would you get a 3D drawn from a 2D simulator? What you do is you define different layers, metals, vias, and then when you draw on those layers, that is interpreted as if it has got a dimension in the z-axis or z-axis, right? So via 4, via 5, conductor via, and then via 6. Okay, so that's also a conductor via. Now I'm going to add one more layer, which I will call as TFR. Okay, and this is a conductor layer. So I'm done with all the layers. Okay, so now if I go from this tab, layers, to layer display properties, I can choose the color for different metals, right? So I would avoid dark colors, but then I would not use gray and white. Okay, so I can use green for that purpose. For white, I can use this one. Okay, so now let's see, everything has a distinct color, isn't it? And just in a bit. Okay, so these are the different colors, and TFR is green color. That's okay, doesn't matter. So this is for ease of your perception, of your view, right? Another thing is that it is going to have patterns, because if you want to have a solid pattern like here, you cannot see underneath, so these layers are stacked up, right? So M0 is the bottom one, then M1, then M2, M3, M4, and so on up to M7, right? So, and then via layers are in between, via 0, via 1, via 2, and so on, right? So they are stacked. So unless you have a certain pattern with a transparency, you cannot see the lower layers from the top view, right? So in this case, I'll start with M0 having the least dense least dense pattern, right? And then I will keep on choosing different patterns, right? So I'm going to use all different patterns available here. And later you'll find that it is the ease of drawing, because of which you are choosing this different patterns. Like, you will be able to debug if something goes wrong if I use this kind of patterns. Okay, so this is M7. Okay, so now we are done with all the metals and their patterns, and these are drawing patterns, right? So this layer has no meaning other than it is a drawing layer. There is no physical meaning attached to this layers any up till now. We haven't attached any physical meaning to these layers. Now if I look at vias, I can keep all the vias as solid the way they are defined. As far as TFR is concerned, I can give it a pattern, and I can give it a real dense pattern if I want to. Okay, like this. So we are done with the layers, their naming, right? We are done with the the role they play, and we are done with the visual aspect of these layers. Okay, so once you say okay, you have those layers done. Okay, another thing is, if I click on any of these, right? So for example, I can click on this and it has been assigned a strip layer which is called conductor. So I'm not going to use that, so I'm going to unmap that. So you right click and unmap. Another thing is that this is called the perfectly electric boundary. So this is basically a perfect conductor here. Okay, so this is I don't want a perfect conductor, so I want to leave it open, right? So I would say delete cover. Right click and say delete cover. Okay, now we will see that we have air at the top, alumina. Now our material is not alumina, our material is borosilicate. That's what LTCC is. So I have to define certain layers which are dielectric layers. So here I can click on this, and then you see in your predefined layers you do not have that borosilicate. And then if I add from database, so there are quite a few options here. You can add a dielectric of your own and then define its properties, or you can add from a given database. Now, do I find here borosilicate? I don't find borosilicate. And the properties of these materials, okay, which are important is ER real. So if you remember in the last session we had this, so this is ER dash or ER real. Okay, so for FR4 it is this, for dioride it is this, for TMM10I it is this, and then this is the loss tangent or the loss. So in a insulating substrate, this is epsilon R double dash divided by epsilon R dash, right? So that's loss tangent. Okay, so we have to specify both of them. Okay, dielectric constant and loss tangent. Now dielectric constant for LTCC. Okay, so let's go into LTCC, and this slide we have seen earlier also. So the left hand side, the blue colored, is your dielectric constant. So it's flat across the frequency from a few kilohertz up to almost 90 gigahertz, right? So if that's so, that value is around 5.85, right? So I am going to put that value as 5.85. right? So if I go back to ADS, okay, so there is nothing which matches 5.85 over here, so I have to create a new one. So I'm going to cancel this. I'm going to say add dielectric, and then I'm going to rename this. I'm going to call this as borosilicate. That's what your green tape is, and it has a epsilon R dash of 5.85, right? And it has got, so I'm not putting the imaginary part of that epsilon because I'm putting 10 delta, so I cannot specify both of them, right? So 10 delta in this case, or loss tangent, what you call, is around 0.002, right? So roughly that. Okay, so I'm going to write this as 0.002. right? So this is your definition of borosilicate. Okay, so once you have that defined, you can go back here and change this to borosilicate. So you have changed this to borosilicate, and then you can add, actually you can insert a substrate layer below. So now this should be borosilicate, isn't it? So this should be borosilicate with a certain thickness. Now for LTCC we have talked about thickness also, right? We are talking about post-firing thickness, post-fire thickness. So right now it's 15.3% of the original thickness. So original thickness is, let's say, 10 mil. So let me open a calculator here. Okay, so 1 mil is 25.4 microns. Okay, multiplied by 10 mil. Is it? Okay, so that is going to be 254, and then I am going to say multiply with is there a bracket I can put here? Let's say if it is a bracket. Oh, it has gone. Okay, so 25.4 micron, okay, is 1 mil. Okay, multiplied by 10 mil, right? So that would be 10 mil. So it will be 254 micron, right? And then I'm going to multiply this by 1 minus 0.153, that is 15%, right? And then bracket close and say equal to. So that's going to be 215 micron. Okay, it will be 215 micron. So that is 0.215 millimeter. Now this is for your 10 mil. Let's look for 5 mil. Let's cancel all or clear all, and let's say we have got 25.4, okay, multiplied by 5. Okay, so that's 127, and that has to be multiplied by 1 minus 15.3%. Sorry, 1 minus 0.153, that is 15.3%, bracket close, and that is 107.569. Okay, well, am I correct in this? No, I'm not correct, because it has to be 24%, right? Not 15. 15 is a XY shrinkage. Z shrinkage is 24%. So let's do this calculation again. Okay, clear this. Okay, so you have got 25.4 multiplied by 5. Okay, and then this has to be multiplied by 1 minus 0.24, bracket close, and that's it. So it should be 97 micron for 5 mil substrate. Okay, so post firing the thickness will shrink down to 97 micron for 5 mil. Now let's see for the 10 mil what's going to happen. 25.4 into 10, okay, multiplied by bracket 1 minus 0.24, bracket close, and okay, so 193 should be the post fire thickness for 10 mil LTCC tape. Okay, so for 5 mil it is 97, for 10 mil it is 193. So let's say I am going to create a substrate like this, right? So here I'm using 97 microns, so I'm referring to 5 mil LTCC tape, right? So this is what I'm going to do. Okay, and then this metal thicknesses. Okay, so if you see post fired thickness of metal is going to be 9 micron. Okay, so let me see material. So basically paint thickness 9 to 12 micron pre-firing and 6 to 9 micron post firing. So I'm going to with the optimistic view of having 9 micron as the thickness. Okay, so this is for your strip lines and microstrip lines. So I'm going to use 9 micron as a post firing thickness of the metals. So all these metals are going to be that. So now here it is borosilicate and it has to be 97 microns, right? And of course here I don't need that, but let me just add a substrate below, or let me make this also. Okay, so this one I'm going to keep as air. Okay, now I'm going to add different layers. Substrate, add substrate layer below. Okay, so how many do I need? I need 7 of them because I have 8 metals. So I'll just repeat it. Okay, so this is 3, this is 4, this is 5, this is 6, this is 7. Okay, so 8 metals, I have 7 substrates in between, correct? And then I have to add metal layers to it. So I can say map conductor layer. It comes out as M0 automatically, right? Okay, so now this is assuming it's a thin sheet of infinitesimally small thickness. right? This is what the method of moment is going to work on. It is not going to work on metal with certain thickness, right? So in this case, okay, instead of perfect conductor, I need to have silver here. I don't see a silver here because it's a silver paste, right? So I need to add it. So if I go here, I have to add from database and look for silver. So right there it is silver there. So I have added silver here. Okay, say okay. So once I have silver here, I can assign silver to that metal 0. Now there are three options here. It's a sheet with infinitesimally small thickness. That's what is required for momentum. Now besides that, there is something called intrude and expand. Okay, so it doesn't matter because it's the lowest one, so I can say intrude into substrate below. Okay, so this is going to be like 9 micron thickness, so let's put a thickness to it as 9 microns. Okay, so we have done metal 0, which is 9 micron thick, and it is intruding below the substrate, below the interface, right, of 9 micron. So the next one, I can map conductor layer as M1. Again, this will be, instead of intrude, it is going to be expand and below, and let's say 9 micron. Okay, so once you do that, what do you see here? What you see here is that 97 is the thickness of the substrate, but then an additional 9 is added. So I have expanded the substrate. Now here I could have chosen intrude. So this remains 97, and this 9 micron is a part of that 97, right? It is not expanded. Okay, so that is what is expected after firing, right? It will be a part of this thickness only. So let's see that. Okay, here, so everything is a extrude. Okay, so it doesn't matter above or lower unless you are going to do a capacitor here. Okay, so what I'm going to do is somewhere in between I'll do a capacitor here. So let's do that. Okay, okay, so you have got M1. So this one M1 is again silver 9 micron. Then I will say right click, map conductor layer. So that's a mistake. Map conductor layer, and that's M2, and again it is going to be 9 micron, right? And it will be expand substrate below. Okay, not expand, intrude. So that's still 97, and when I reach here, I am going to put the top one, right? So I'm going to say map conductor layer, that is M3, and that's having a thickness of 9 micron, and that's intrude into the substrate above. Okay, so now you notice that this 97 micron is clear 97. It doesn't include thickness of any metal, neither M2 nor M3. Now if I was to do M4 here, map conductor layer, and do it at 9 micron again. Okay, so this one is 9 micron. Okay, 9 millimeter, wrong. 9 micron. This is 9 micron. So all are 9 micron, right? This is 9 micron. This one is intrude below, and it is 9 micron. So now if I make a capacitor between M3 and M4, that is going to be 97 minus 18. Okay, it will be 79 micron as the gap between the two metals for making a MIM capacitor here, right? So then I can put here other layers, and let's say this is going to be metal 5, 9 micron, and intrude above. Then another one over here, that's again 9 micron, and intrude above, and finally this is going to be 9 micron, which is M7. So these are 8 metal layers, right? And this is going to be again 9 microns. Okay, and this should be intrude above, right? So let me check all of them. 9 micron, 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 and 9 micron. So all of them are 9 micron. Now I'm going to insert via. So I'll right click on this one and say conductor via. So it is going to put in via 0. It is automatically take the numbering via 1. So before that, let me say that I'm not going to use a perfect conductor. I'm going to use AG, right? So same thing over here, I'm going to use AG. Okay, so that's via 1, that's via 2, that's via 3, that's via 4, that's via 5, and that's via 6. Okay, so now somebody would say, where do I keep my metal? Okay, it depends on your screen printing, right? You can keep your resistive metal TFR anywhere, right? So I can keep that TFR somewhere in parallel with this. So I can say map conductor layer, not the via layer, not the whole. So unmap that. Over here I have to map a conductor layer, and that's called TFR here. Now I'm going to say intrude above, and this one is also 9 micron. Okay, but for TFR we don't have a material, we cannot use AG. So if you go here, we have no material. So I'm going to create a add conductor, and here I'm going to say TFR lay or TFR layer. Okay, so TFR lay, I want to put here a resistivity or a resistance. So when I do resistance, it will come as ohm per square, and let's say this is going to be 100 ohm per square. Okay, so because we are going to use a paste of certain resistivity, so this one in screen printing we are going to use a paste, so it depends on that. So if I go to materials, okay, so that is called FX87101. so this FX87101 is basically your paste, just like your silver paste, right? For screen printing of the traces, this is a paste which provides you a resistivity, post curing a resistivity of 100 ohm per square. So that's that, right? So once we are done with it, our substrate is ready. Now don't worry about cavity, because we are not going to deal with resonant cavities here, right? Okay, so let's say our substrate is now complete. Okay, so that's done. And for TFR, I'm going to choose that TFR lay, which is going to be a resistivity of 100 ohm per square. So our substrate is complete, and say save. Now we have a substrate now for LTCC process, which is a 5 mil process, right? Okay, so we are done with this. We can close this, right? Now we are ready to draw. Okay, so first thing I'm going to draw is lines. Okay, so let's go to the environment now. Now this is the main window of ADS, and you can create a cell with a default view of substrate, with a default view of layout, with a default view of symbol. So I'm going to create a cell with a default view of a substrate, or of a schematic, right? So here the default view is schematic, and I call this as line 50, line 50, correct? So I want to make a 50 ohm line, so I can put here ohm also, and here it is a microstrip line, so I'll put here a micro. Okay, so it's a micro line, 50 ohm, create schematic. Okay, so now in this schematic you are not going to do layout, right? This is just a schematic, but I opened this for a purpose. I opened it to launch a tool here called line cal. Okay, so I start a line cal. Okay, once you start a line cal, you have provided this window. Now I want to make a CPWG. Now this is a microstrip line. Okay, I can make a microstrip for the ease of drawing. So let's say I'm going to make a microstrip line, then CPWG. Okay, so I can choose that from here. Okay, I can make a coax also. So let's make different lines. Okay, so right now it is amblin, which is represents microstrip line. Epsilon r is 5.85. 5.85, right? Mu is 1 because it's non-magnetic. Height is going to be 97 microns. Okay, height is going to be 97 micrometer, centimeter, millimeter, micrometer. Okay, this height is the box height. I'm going to not change it. This is the metal thickness. Metal thickness is going to be 9 micron. Okay, and this is the conductivity. Now if you take silver, silver has the highest conductivity of 6.17 e raised to 7. Okay, 7s per meter. So that's that. Now the loss tangent, okay, for this this borosilicate is 0.002, as we have figured out. So now we have the substrate entered on this column. We have put the dielectric constant, we have put the height of the substrate, we have put the thickness of the metal, we have put the conductivity of the metal, we have put the loss tangent of the substrate, borosilicate. Now we want to design, let's say, a line at let's say 10 gigahertz. Okay, so that's going to be deciding the length. Now here I want the units to be millimeter, so let's put them to be millimeter, and I am going to design a 50 ohm line. So not 60, 50, sorry, 50, and I want the effective length to be 90 degrees. Now this is not going to be very accurate, but this is going to be close. And when I say synthesize, okay, so it should give me the values over here. Okay, so that means if I have a line of 140 micron width or 0.14 mm and a length of 3.7 mm, that would be a 50 ohm line on this substrate, which is 90 degrees. So let me draw this on M7, right? So let's do that. So we should know these numbers. So I'm going to just do a screenshot of this. New. So this is our screenshot of this. Now on the right hand side you can also see that it says that it is going to have an effective dielectric constant of 4.0, and then it is going to have the loss of 0.06 dB, and the skin depth is 0.025. okay, so that's that. Okay, so we are going to keep this aside, and now I'm going to draw the line in momentum. Okay, I can close this. I need not save this. That's okay. I have the information there. Okay, so this is going to be blank. I'm not going to do anything over here. But when I go to ADS main window, in this cell, I'm going to add a layout view. Okay, so a layout view for that. So now first thing over here is you have to be conversant with what is this. Okay, so there are certain drawing tools at the top. So this is a toolbar. Okay, so these are regular windows, save, open folder and all that stuff. This is your cancel, or this is going to be deleting something, right? And then this is undo and redo commands. Then this is view all the entire geometry to the extents of geometry you have drawn. That will be zoomed in to the extents of geometry. That is view all. Or you can zoom in any section. You can use the scroll wheel of the mouse. So this is the scroll wheel of the mouse which is doing this. Then you have got copy a component. So this is going to be making a copy, while this one is going to move it. So this is move the component, this is make a copy of a component and then move it. Then this is going to be rotate. This is mirror about your x-axis, this is mirror about your y-axis, right? Now these are the snap grid options. So in drawing, when you move this mouse, it moves freely, right? But once you start drawing, this mouse will be attracted to one of these smaller dots, right? So this is called snap to grid. So when you try to place a point for drawing, it will automatically attach it to one of the dots on the grid. Okay, so that will be called snap to grid. So that's a snap to grid option. You can turn it on, turn it off. Now grid is very important. Because everything is done through screen printing, right? So if it is screen printing, there is a mesh size for the screen, right? That basically is going to be that grid. Okay, then this is snap to the edge. So if I draw two objects, so for example, I can, okay, before I do that, I will adjust the grid. Okay, so right now this is going to be in mm, right? So if I go to options, I go to preferences, and here if I go to snap grid options, okay, so it says right now I'm going to use 0.1 mm grid. Okay, so I'm going to make this as 0.01 mm grid, and then it says minor grid is going to be one grid cell, which is, so that's basically distance between these two lighter dots. Okay, so that's that. And then major grid is five minor grids. So you see these bright dots are major grid, while the light dots are minor grid. So 5 minor grids makes a major grid here. So I'll leave it at that. When I hit apply, of course, you see it's disappeared, but you have to zoom in to see where that is. Now if I do these changes for this layout, I have to do this for every layout, alright? But to avoid that, I can save a copy. Okay, so I can save a copy as a layout preference and say save. So now next time when I open a layout window, all these settings will be, grid settings will be automatic, right? They will be, as I set it here. So you have to save this to a layout preference file. Okay, and you click OK. Now if I zoom in, I still have that grid. You can see there, this is 0.01 micron here, 0.01 mm, sorry, 0.01 mm, and then this distance is going to be 5 such grids. So that is going to be 0.05 is the distance between the two points on the major grid. So there is a minor grid and then there is a major grid. So once you are done with it, now you can draw on different layers, and the layer you are drawing on can be chosen from here. So if I want to draw on, let's say, M7, so that's that. You can choose your layer on which you are drawing. So if I look at here, okay, I'm drawing a structure on M7 here, and my ground plane is going to be M6, right? Okay, or you can choose M5 and M6. The distance matters, is 97 microns. Okay, so M5 and M6, this is going to be a strip line, while M7 is a microstrip line because it has air, okay, on the top and the substrate bottom. So the way we did a line cal is for a microstrip, not a strip line, right? So I'm going to draw this on M7. Okay, so I have chosen M7 here, and my drawing tools are over here: rectangle, polyline, then a polygon, and then a trace. Okay, so I can draw using a trace if I want to. So I can say trace, and then you say the trace end style, I can keep it to be truncated. Okay, and the rest I don't bother. Only thing is I want a width. So the width I have computed to be 0.140, right? So 0.140. So I can put here 0.140. Okay, so that's the width. and now I can draw. So if you see, if I move the mouse is going to move from tick to tick or dot to dot on a minor grid. So this is called snap to grid. Okay, so if you bring your mouse closer to one of these dots, the mouse will automatically move to that dot. So that is called snap. So I can put here, this is 0 0, right? So the location is 0 0 here, right? So I can click once here, and I'm drawing on metal this, and I want 3 mm. Okay, so the length here is 1.26. So if I go here in my drawing, I want 3.71. Okay, so I want 3.71. So this is 2.9, 3.71. Sorry. So 3.77. I can zoom in. This is 3.71. Done. If I click once again, it's going to put a corner. But if I click it twice, okay, then it's going to finish line. Now this one is called a trace. This one is not a metal structure. It has a width, right? It has a width. Okay, and to measure the widths or distances, I can right click anywhere on this window and say measure. And when I say measure, I can move from this corner to that corner. But you see, but my mouse is going to snap to the grid, okay, not to the corner. So there is a snap corner option here. Okay, so this is snap corner. Okay, and this is snap to intersection, or snap to intersection, and this is snap to the edge. So with this snap enabled, you can go for once here, click one there and one there. Okay, so you will know that this is 0.14 mm, right? That's what I have drawn, right? But this is still a trace. So to convert this into a metal, you can always convert this to a metal. So the way to do this is I can go edit, flatten component, and flatten it out, and say flatten one level of hierarchy, say okay. Still okay, let's see, convert it to trace. Okay, still that is there. Okay, another is, if this is not working, merge union. Okay, so now it has become, from trace, it has become a rectangular piece. Okay, this is no longer a line, this is a rectangular piece of metal, right? So I have drawn on M7. Then I'm going to draw on M6 the ground plane. Okay, so if you look at line cal, okay, so you see the bottom one is the ground plane here, right? This is a ground plane here, right? Hang on a second. Okay, sorry about the interruption. Okay, so now, okay, so this thing is all ground plane, right? So this thing underneath is all ground plane here, right? So this is all ground plane. Okay, so I don't want to, there is no undo on this one. It doesn't matter, it is just for our purposes. So this is a ground plane, so we are supposed to draw a ground plane on M6. Now I'll tell you this, the size of the ground matters, okay, the extent of the ground matters. So the extent of the ground is on the top and the bottom. So if I choose metal 6, okay, let's choose metal 6 here, and I make a metal 6, let's say we have a snap to here, so that's a metal 6, and let me do a structure up to here. Okay, it's short. Okay, so you can always have this handle and stretch it to the, so now the length of this is quarter wave, right? Now I can rotate this out. Okay, so I want this to extend of this. So what I want to do is I want to align this somewhere here like this, and I want to extend this up to the edge. So this is snap to corner, right? So this is one side extent. I can copy this, and to copy this, you have to just select this and click on copy button, and then snap to this corner. So snap to this corner. You can use the zoom out and then go up and place one over here. So now you see that my extent is going to be twice of 3.71. So if I want to measure this, I can measure this from this. Okay, snap here, and I can go and snap here. So this is going to be twice of 3.71, right? So that's what I mean by extent. Now what it means is that if this is an open condition, then that looks like a shot here. Okay, so I am going to just select both of them by pressing shift. I can select both of them. So I press shift, select this one, select that one, and I can say right click, not here. Maybe I can go to edit, merge, union. Okay, so now these are the merge commands. Like, these are your layer wise Boolean operations. So what did I do? I did a union of two metals to get one metal. Okay, so now that metal extends quarter wave on the top and quarter wave on the bottom, and the length is quarter wave, right? So this is the microstrip line. Okay, so once you have drawn the structure of a microstrip line, okay, you are going to put ports. Okay, so here what is important is I'm going to put all the signal ports first. So if I go here and if I snap to center, it will automatically change the color to the line, so which is going to be your metal 7. Same thing I'm going to do for a port here. Okay, done. So now I have two ports for the signal, port 1 and port 2. Then I will need a ground reference. Okay, so I am going to do a snap to edge. So this is 3 is a ground reference for 1, and similarly I'll snap to there. This is a ground reference for 2. Okay, now I can move this underneath the first one. So this is move. I can hold from here and move it under here, and you might have a line. So right now it's not there. Sometimes you get a line here that you move the port from here to there, so you have to delete that. So now you see 3 is going to be below 1. Similarly over here I can move this. So I'll just zoom in and snap to this pin and then place it here. So 4 is underneath 2. So now 3 is underneath 1 and 4 is underneath 2. So now my ports are 4 in number, and I know that microstrip line has got 2 ports, but these are ground references. So they are local ground references. So what you have to do is, you already know the substrate. So if you click on substrate, this is what you define. So that substrate is over here. There is a symbol. Then you have to create EM simulation first. EM simulation settings. So you click on this button and say EM setup, say create EM setup, and dismiss this window. Now here, if you go to ports, right here, this is a port editor. Okay, so this is a port viewer. So I have to open an editor. So if I open an editor, okay, so what do I see here? I see I have got 4 ports, but I know that 3 is a ground reference for 1. So I'll take the positive of 3 and drag it with the left mouse button clicked, press down. With the left mouse button pressed down, I drag this plus of this port 3 to ground, or minus of port 1. So now 3 is a ground reference for 1. Similarly, I can take 4 and drag it to ground reference here. So 4 is a ground reference for 2. So 3 is a ground reference for 1, 4 is a ground reference for 2, and we are done with this editor. We can cancel it. Now you can just save it once, open this EM setup. It says that ports have changed. Yes, they have. Now I've got only 2 ports. Port 1 is reference to 3, 2 is reference to 4, right? So once you do that, your ports are defined. So substrate is over here, everything is fine. Ports are over here, fine. Now what frequency do I want to simulate. So I designed this for 10 gigahertz. So I'm going to do a single point and I'm going to put here 10 gigahertz. I'm simulating for 10 gigahertz, correct? Next is output plan. So here I want to save the currents for all the frequencies which are simulated. Okay, so that's the output plan. Next is options. So here you have to go to mesh, and in case of transmission line, two meshes are important: edge mesh and transmission line mesh. And if you leave this to 0, it will automatically do the meshing. Okay, you do not have to specify how many cells per wavelength. Okay, so what does it mean? It means that in a microstrip line, all the currents are on the edges because of the skin effect. Okay, the current at the center is very less, right? We will see in the simulation. So that's why this edge mesh is important, right? And then there is a transmission line mesh which will be along the length of the line. You know, how many cells do you want to put? And I have put this on automatic by putting 0 here. Okay, so options, mesh, edge mesh, transmission line mesh, that's done. The next thing is model. So once you have done the simulation, it should automatically create a model. So you should check this one, ensure that EM model exists when the simulation is launched. Okay, so this is done. So now we are done. We can save it. So EM setup is saved. Okay, what did I do? Let me summarize. I made sure that my substrate is correct. I might have 2 substrate, so I will be able to choose among the 2 here. Okay, so that's substrate. Then I went to port editor, specified what is the ground reference for the 2 signal ports. Then I set the frequency as a single point simulation. Then I set the currents to be saved for all the simulated frequencies. Then under options I went to mesh and said that I want to enable edge mesh and transmission line mesh, right? And then I went to model and I ensured that the model is created once the simulation is launched. And here, okay, there are different options here, but I am going to compute S parameters. So it is automatically going to mesh first, then compute green functions, right? Green functions are for the substrate, and then mesh. Now, what are green functions? Okay, if you take a matrix and you want to invert a matrix, right? You are going to do n cube operations to invert a matrix by direct method. Okay, so you are going to use n cube for inverting a matrix of size n by n cube operations. Now if you express, okay, structure in terms of a different basis vector, not x, y, but in terms of, or rather, you know, you say, how would I explain that? Okay, so there are certain basis vectors, right? And you want to transform this substrate information in terms of those basis vectors. So once you do that, you do a inverse of a basis vector rather than inverse of a matrix. And when you do the inverse of a basis vector vectors, then the solution of inversion is just a matrix multiplication rather than a matrix inversion. So that's going to be basically n square operations. So that's how, you know, this works. So first it is going to compute green functions, which are nothing but the basis vectors, and then it will know the inversion of basis vector matrix, and then it's going to multiply this with the coefficient matrix to invert it. So the matrix inversion is reduced down to matrix multiplication. That's what happens with green functions. So when I hit simulate, so it is going to first come and say that I'm going to compute the substrate, and that substrate I'm going to compute around 10 gigahertz, right? So this is a single threaded operation here. This is not multi-threaded. So this is going to take time. Even if you have a multi-core machine, it is going to take the same amount of time almost. So you have to sit for the substrate computation, and this green functions are computed once. Okay, unless you change the stack up, unless you change the stack up or something in the metal stack, this is computed only once, and then the next simulation will not compute it. It will have it. Okay, so substrate calculation has started, and this is a single threaded process. Okay, that's why it is going to take same amount of time irrespective of what machine you are running on. unless you have a high frequency processor, right? Okay, so now this is done. Okay, so now after it is done, okay, don't worry about the warnings, we'll talk about that later. So what did we do? What did it do? It mashed it. So it mashed metal 6. It also mashed this line, but you see here it has put the single cell size mesh on the edges, and then it has put these many cells. So there is something called adaptive meshing here also. It tries to minimize the mesh because it wants to keep down the computation volume. Another thing I want to tell you is under EM simulation there are two options here. Okay, one option is called microwave momentum and then momentum RF. So whenever you put a metal on a semiconductor or a metal on a dielectric material, metal on a dielectric material interface, you will put energy into surface waves, and that surface waves have to be computed. That will happen in microwave momentum microwave. But if you want to not compute those evanescent modes or the surface waves, you can check momentum RF. Okay, it will be faster but it will be less accurate. So I always keep on momentum microwave, right? Okay, so we are done with this. Now there is another thing. Before even you do the simulation, you can check whether my geometry is correct or not. So this is called 3D EM preview. It doesn't matter whether you have done the simulation or not, you will still be able to see the 3D view. Okay, so for 3D view you have to have a substrate defined and EM setup done already. Then only you can do this 3D EM preview. From the main window also there is a 3D EM preview over here, right? So I'm going to check on this one and it is going to open a 3D window. Okay, so if you look at this 3D window, okay, what you will see is this is metal 6 and this is your metal 7, and this is, you are looking at port 2 and port 4 is not labeled here. Why? Because port 4 is a ground reference for 2, so it is going from ground to the signal. Okay, similarly over here port 1, sorry, let's zoom out. Okay, port 1 is ground reference to 3, so the 3 is removed, only 1 remains. So what's the rule? The rule is first you put all the signal ports and then you put all the ground reference ports, because ground reference ports are going to be removed. Now let's say if I did 1 as a port and 2 as a ground reference, 3 as a port and 4 as a ground reference. So what will happen is it will remove 2 and I'll be left with 1 and 3. 2 and 4 will be removed. So this is not continuous. 1 and 3 is not continuous. So to maintain it continuous, you will first put the signal ports as 1 and 2 and then 3 and 4 is the ground. So ground ports are put at the end so that when they are removed, the sequence of signal ports is not changed. 1, 2, 3, 4, 5, 6, they remain in sequence. So you understood what do I mean by that. So that's your EM preview. Okay, there are other layers also, but there is nothing drawn on them, right? What is drawn on is metal 6 and metal 7. Okay, another tool I want to tell you is this is called the connectivity tool. So for example, let's say in a complex geometry, I'm not sure if this line was shorted to the ground. So if I click on this and click on this one, so it says that only this yellow is highlighted. Okay, so let's move it. So only yellow is highlighted while the metal 6 is not highlighted anymore, right? So that just shows that there is no connection of metal 7 to metal 6, okay, in this geometry. Same thing if I put on metal 6 over here, hang on. So it says metal 6 is highlighted here, right? But then it has no connection with metal 7. So that's why it is completely transparent. Okay, so this is solid connectivity tool. Okay, this is helpful in number of cases when we do the layouts, right, so as to make sure that one metal is not shorted out to the other metal. Usually happens with the capacitor, right? So that's why there is a solid connectivity tool here. So it doesn't matter. Okay, so we are done with this window. We'll close this. Now once the simulation is done, I can look at the results, right? So it automatically opened the results here. So this is a template. It has used a certain template. I don't worry about template. I'll just zoom into an empty region and I'll put here a Smith chart from the left hand side. So you put a Smith chart and you plot S11 and look at it. So S11 is not 50 ohm, okay, but it is close. So if I put a marker on here and marker here and I look at this S11 and if I double click it, I can go to format and say normalize to 50. So it is going to look at 53.2 ohms rather than 50 ohms. So it's 3.2 ohms extra. Okay, so similarly if I put S22 is underneath that only, right? And let's look at whether it's a quarter wave. So if I put a rectangular plot here and plot phase of S21, so I add S21 phase. Okay, so that is 90. There is no problem with the phase. That's approximately 90 degrees for 10 gigahertz. So what I'm saying is LANCAL is not very accurate in this sense. Okay, so, but I would not change this for now, right? So this is there. Now another thing which you can do is is visualize currents. So you can launch from here or you can launch from here. They are the same things. So if I go here and say visualize current, it's going to open the same 3D structure. Okay, but this time it is going to put in currents. Okay, so you are going to see these currents. So I'm putting the power in port 1. How do I know that? Okay, if I go here in solution setup, I have chosen port 1 where I want to put the power and I have chosen frequency as 10 gigahertz. That's by default here. And if I go to properties, plot properties, I can animate this. I can animate this current. Okay, so to animate it, I just click on animate. Okay, so this is a quarter wave. So what you're seeing is that power goes in from port 1, goes out on port 2, right? Now if I want to change the legend of color, I can make this one as 1. So now you can see clearly in terms of colors. So this is too little. Let's put here 3 or 4. Okay, so power, the red represents the high current density. Okay, and the blue represents the least current density, right? Okay, so that's what it is drawing right now. Okay, so that's drawing the currents in. So you would see this. You would see that the currents on the edges are red colored because the currents are concentrated on the edges only, and then the bottom, right? While in the center of the line, the currents are not there or very little. Most of the current is going to be on the edges. Now another thing you'll notice is that in the ground plane you are also seeing currents. Okay, that's why the voltage is not 0. Okay, so you have to be very clear. If you draw structures which are of the order of wavelengths, okay, so this is a quarter wave, so this is of the order of wavelengths, then the currents in the ground plane are not going to be 0. They are going to be return currents, and because of the return currents there is going to be a bouncing voltage. Okay, so the ground is distributed. The ground is not 0 volts, right? And your whatever is your impedance, the impedance is relative to the local ground. So whatever is the ground voltage here, the voltage of the signal is with respect to that ground voltage divided by the current will give you the impedance here. So the impedance of the line depends on the local ground. So you see here port 2 has its own local ground and port 1 has its own local ground, and this is not a 0 volts because the ground plane has got currents. You can see here You can see here the ground plane has got currents, right? So this is what is important when you do a high frequency anything, board design, chip design, MMIC design, right? You have to be considering the ground to be distributed, right? Now there are other ways of drawing this. Okay, if you go to arrow, enabled it. Now these are two big arrow. Okay, so you see the currents are reversing directions, right? You can see instead of colors shaded region, you can also put arrows to see that. Another thing is contours. Okay, so it is going to draw contours. It might be, should be able to give height to it. Okay, so let's increase the divisions in the contour. Okay, so now you can understand what contours are doing, right? So you can have shade, you can have arrow, you can have contours. You can slow this down. Okay, basically you can say phase increment of 5. Okay, so this is going to slow down a little. Okay, so now you can see that the propagation of wave is from the input port to the output port, right? Okay, so with this, I guess I have explained you how to set up a structure for simulation in ADS, right? Or momentum, right? Okay, so I'm going to close this. You can experiment on your own, and I'm going to stop here for session number 3. It's already 1 hour, right? Thanks a lot. Thank you.